Hi everyone, today we're going to start our two-part video series on finding the derivatives of the 6 trigonometric functions. And today I'm going to keep it really basic. We're just going to do like sine x, cosine x, tangent x. We're just going to do trig function with just an x in it. We'll deal with more complicated trig functions in a different lesson. But for today, we want to establish why like the derivative of sine x is what it is, and so on through the 6 trig functions. So we're going to start with sine x, and I'm actually not going to do this proof analytically, although we could. It's not too terribly hard, especially with our work from Unit 1 with limits. But I actually like doing this one better visually. It's just a nice little way to see what the derivative of sine x is. So what we're going to do, and you did this in pre-calculus, is we're going to graph one cycle of the sine curve. So I've kind of laid out the x-axis here as if I've unraveled the unit circle, and I picked the highlighted points here. So I've got my 0, I've got pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. And then I also have my y-axis up to 1 and -1 because I know my sine is trapped between -1 and 1 inclusive. So let's just go around, and I've also highlighted in red the coordinates here, and we know that the sine of any value we plug in, any of these x values, is going to be the y coordinate. So we're going to be focused on, ooh, that's running a little bit, the y values here. So if I plug x as 0, if I go to 0 radians and look at the second coordinate, it's 0. So the sine of 0 is 0. I'm going to plot a point there. And if I go to pi over 2 to the top, the sine at pi over 2 is 1. So I have a point at pi over 2, 1. And then over to pi, I'm back to a sine of 0. 3 pi over 2, -1. And 2 pi, 0. So this is one cycle of the sine curve, and this probably looks very familiar. And if I went further, this would become periodic because as I wrap a second time around the circle, all those values are just going to repeat, and again, and again, and again. So we're just going to look at this one cycle. Now, we're going to use the technique we learned the other day, sketching derivatives given original graphs. So we're going to evaluate the slopes of the tangent lines along this curve to see if we can construct the graph of the derivative of sine x. So what I'm going to do is take my ruler, I'm going to go along these marked points, and I'm going to draw tangent lines. So for example, if I go to 0, now remember, I know that this would also come back this way. So if I draw a tangent line here at 0, going to look like this. If I draw a tangent line here at pi over 2, it'll be horizontal. If I draw a tangent line at pi, it'll be negative. If I draw a tangent line at 3 pi over 2, it's back to horizontal. And at 2 pi, it would be back to positive. So my slopes, m is positive, m is 0. M is negative, m is 0, and then m is back to positive. Okay, so just kind of hold tight with that for a second. So that's where we are right now with y equals sine x. Now what I want to do is the exact same thing, but I want to do it with y equals cosine x. So we know that the cosine is the x coordinate around the unit circle. So now we're kind of focused on the first coordinate. And so when I go to 0, my cosine there is 1. So I'm up here. And when I go to pi over 2, my cosine is 0. At pi, -1. At 3 pi over 2, I'm back to 0. And at 2 pi, I'm back at 1. So this is what one cycle of cosine looks like. And again, that will just kind of arching that because it's just going to repeat itself. Over here, it's going to repeat itself. And if I go through and grab the slopes of the tangent lines at these sort of marked dots, I'm going to start here at 0, 1 with horizontal. At pi over 2, it's going to have a negative slope. At pi, back to 0. At 3 pi over 2, positive. And then at 2 pi, 0. Okay, so my slope is 0. Slope is negative. Slope is 0. Slope is positive. And slope is back to 0. Nothing too crazy so far. Okay, now let me bring sine x back here. Okay, so here was our sine x graph. Now I'm going to change to yet a third color. Let me use blue. Hopefully this will show up. And I want to now transpose the derivative graph. So now I want to graph y prime. Y prime against x values is going to be here in blue. So this is y prime in blue. And this isn't going to be exact necessarily. I'm just trying to get the gist here of the shape of the derivative graph. So let's come to 0. So at 0, the slope here is positive. So I'm just going to plot some positive value as the slope here. Okay, moving over to pi over 2. The slope is 0. So at pi over 2, my slope is 0. See, the ordered pair pi over 2 comma 0 would represent at pi over 2, the slope is 0. At pi, negative. At 3 pi over 2, back to a slope of 0. And at 2 pi, back to positive. So when I connect these dots, this should look like the graph of the derivative of y equals sine x. Now take a look at that. What does that look like? What does that blue graph look like? Well, I think it looks like, I can get these both on here. I think this blue graph looks like cosine. See, cosine, blue graph, cosine. So we've just shown graphically, visually, that the derivative of the sine of x is the cosine of x. So that's what I'm going to write on here. So if y equals sine of x, then y prime, it seems, is cosine of x. So just keep that in mind. Okay, now let's go to our graph of cosine x. Here's cosine x. So we're going to, in blue, we're going to graph y prime. And we're going to follow these slopes. So at 0, the slope is 0. So my y prime graph would have a point at 0, 0. At pi over 2, negative. At pi, back to 0. At 3 pi over 2, positive. And at 2 pi, 0. So that graph, if I connect these dots, is going to look like this. Kind of go over this a little bit darker with the blue. So what does that graph resemble? Well, I don't remember a graph dipping down first. I haven't done anything today anyway like that. But if I look at sine, now think about what sine normally looks like. Doesn't the sine graph, if you look back at the original sine graph we made here in purple, the original sine graph looks like this. I'll dash it just to kind of make it stand out a little bit more. So this is the graph of sine. So all we've done is taken the sine graph and flipped it over the x-axis. See, this part is now this part, and what was down here is now up here. So we've basically made all the y values their opposites. And lo and behold, if you start with y equals cosine x, the derivative of cosine is sine x, but the opposite of sine x, so negative sine x. Keep that in mind. Just knowing these two little rules here and here will get us through the other 4 trig functions. So check it out. I'm going to show you now y equals tangent x. Okay, so how do we prove the derivative of tangent x? I'm not going to do this one visually. I am going to do this one more analytically. So here's the process. Are you ready? Step by step. Y equals tan x. Well, first I'm going to rewrite that as the quotient of sine x over cosine x, because that means the same thing as tangent. Now, knowing what we know, we already have the derivative of sine, and we have the derivative of cosine from our graphs, and I'll remind you of those here. So the derivative with respect to x of sine of x, we know to be cosine x. And the derivative with respect to x of cosine x, we know to be negative sine x. So keep those in mind as we do the quotient rule. Okay? Quotient rule we already know from past lessons, so here we go. The quotient rule says, first step, you take the denominator times the derivative of the numerator, and the derivative of sine is cosine, minus the numerator times the derivative of the denominator, which is negative sine, all over denominator squared. So that's step 1 of quotient rule. Next step, little simplification. Cosine x times cosine x is cosine squared x. Negative sine x times negative sine x is positive sine squared x. And this is still all over cosine x squared. Now, from the green sheet I handed out long ago, some of our trig identities. I've highlighted the one we need here. The Pythagorean identity says that sine squared theta plus cosine squared theta equals 1. So I'm going to replace cosine squared x plus sine squared x with 1. So now I have this. And we know that the reciprocal of cosine, 1 over cosine, is secant. So I'm going to rewrite this as the secant of x quantity squared, or you can write it without parentheses as secant squared x. So that is the derivative. The derivative of tan x is secant squared x. Okay, now the other 3. So we're talking about cotan, secant, and cosecant. I have those somewhere here. Oh yes, right here. I have them all written out for you, okay? Here is cotangent. All the work. Final answer. Here is secant. Final answer. Here is cosecant. Final answer. You can pause the video and you can analyze these and really look through. I do a rewrite, a quotient rule, simplification, a rewrite, quotient rule, and so on. So pause the video, check it out, and that is going, actually you don't even have to pause the video. I mean, you can. This is the end of this lesson, part 1, because this lesson has now shown the derivation of all 6 formulas, and in the next video we're actually going to use the formulas to do some derivatives.